We've seen how it's possible in infinitely repeated games to support action profiles that aren't Nash equilibria of the stage game as subgame perfect equilibria. The reason is that we're able to leverage the long shadow of the future to build reputations or relationships between players and use the threat of falling back to a Nash equilibrium as punishment for breaking cooperation. But the question still remains, what are all the possible payoffs that you can achieve in a subgame perfect equilibrium? So that's what I want to talk about in this video. So let's start by looking at another version of Prisoner's Dilemma. It's pretty much the same game. The preferences of the two players are the same. It's just I'm going to give you different numbers that'll make it easier for us to work with. In this version of the Prisoner's Dilemma, the payoffs to each of the players from cooperating is 4, and the payoffs to each of them from not cooperating is 0. Now the payoff from defecting when your opponent cooperates is 6, while your opponent gets -2. So this is still a version of Prisoner's Dilemma, we've just changed the numbers. The Nash equilibrium of the stage game is still DD, and so the Nash equilibrium payoff is still 0-0. If we wanted to support 4-4 as a cooperation payoff, in other words, if we want to support the action profile CC, we can check how high delta needs to be in order for us to be able to do that. If we wanted to support CC as an SPE, using the notation from the previous video, the cooperation payoff would be 4, the punishment payoff would be 0, and the deviation payoff would be 6. We need to check that delta is at least UDI minus UCI divided by UDI minus UPI, which is 6 minus 4 divided by 6 minus 0, which is a third. So as long as delta is at least a third, the Grim Trigger strategy is a subgame perfect equilibrium. But what we want to know is what else can we do? What other payoffs other than 4-4 can we achieve? There are many other subgame perfect equilibria. Rather than talking about what the exact equilibria are, because there are many of them, many different strategies would yield the same payoffs, we're going to talk instead about the payoffs. To talk about the payoffs, rather than talking about the lifetime payoff, what we're going to actually talk about is the average per period payoff. So I'm going to define for you the average per period payoff. Given a stream of payoffs, what is the average payoff that you get? Of course, when I say average, I mean average per period. To answer that question, let's think of it the other way around. Let's suppose you get A in every period. Then your total payoff is A over 1 minus delta. So what is the average amount you got in each period? Well, it's just A, because in every period you got A. So if you want to go from your total payoff to the average payoff, we can just multiply by 1 minus delta. So if your total payoff is V, then your average payoff is just 1 minus delta times V. So think of it this way. If you got 1 minus delta V in every single period, so if you got the average amount in every period, then your lifetime payoff would be 1 minus delta over V divided by 1 minus delta. So it would just be V. So now we can ask the question, what are all the average per period payoffs that you can get for some sequence of action profiles? And it doesn't matter whether those sequences of action profiles form subgame perfect equilibria or not. We just want to know what average payoff vectors are even attainable. Well, we can draw a picture of what those payoffs are. Here, we've plotted on the horizontal axis the utility of player 1 and the vertical axis the utility of player 2. The utility that they both get from the action profile DD is 0 each. From CC, they get 4 each. From CD, they get -2 and 6 respectively. And from DC, they get 6 and -2 respectively. When we look at the diamond formed by those 4 points, to be more technical, when we look at the convex hull, in other words, when we just look at all the points between these 4, those are the payoff vectors that can be achievable. These are what we call the feasible payoffs for this game. Let me give you one example and demonstrate why that's a feasible payoff vector. Let's take, for instance, the payoff vector 5 for player 1 and 1 for player 2. 1 and 5. That's going to be right on this line. So I claim that 5-1 can be achieved by a particular sequence of action profiles. And what action profile sequence attains that? Well, we can attain 5-1 by alternating between playing CC and DC. Let's check that. 1's total payoff, if we alternate between CC in odd periods and DC in even periods, is the following. 4 plus 6 delta. In the first period, she gets 4. In the second period, she gets 6 delta. In the third period, she gets 4 delta squared. In the fourth period, she gets 6 delta cubed, and so forth. Her payoff alternates between 4 and 6. I can factor out 4 plus 6 delta and write this as 1 plus delta squared plus delta to the 4 and so forth. Right? So I'm going to group these guys into pairs. I'm going to factor out 4 plus 6 delta. So in the first term I am left with the 1. For the second grouping I'm left with the delta squared and so forth. This thing here is just 1 over 1 minus delta squared. But remember the identity that 1 minus delta squared is 1 minus delta times 1 plus delta. So that's 4 plus 6 divided by 1 minus delta times 1 plus delta. So what's the average per period payoff? Well, the average per period payoff is going to be the total payoff times 1 minus delta. So it's just 4 plus 6 delta divided by 1 plus delta. We could do a similar analysis for player 2. And player 2's average payoff is 4 minus 2 delta divided by 1 plus delta. Now if we take the limit as delta gets to 1, we approach 5 and 1 respectively. So what this says is that depending on how close you want the payoff to be to 5, if player 1 is patient enough, that payoff is going to be close enough to 5. Similarly, the limit as delta goes to 1 of 4 minus 2 delta divided by 1 plus delta is 1. And again, that says as delta approaches 1, for delta high enough, the average payoff of player 2 is going to be 1. So in this way, everything in this shaded area is attainable by some combination of action profiles. So by alternating between them in some complicated way, you can get to anything in here. Now you might ask very reasonably, okay, so all of these are attainable by something, but which ones are actually attainable by a subgame perfect equilibrium? And the answer to that is anything that is above DD. Because remember, DD is the payoff that you get in the stage game Nash equilibrium, and any payoff vector in the shaded area that beats a stage game Nash equilibrium can be attained. So anything in here can be attained as a subgame perfect equilibrium average payoff. The reason is because you can use this Nash equilibrium of the stage game as the punishment. And you can follow the pattern of action profiles. For example, for 5-1, you would alternate between CC and DC until somebody breaks the pattern. As soon as somebody breaks the pattern, you punish them by dropping down to the stage game Nash equilibrium, which is DD in this case. And then you punish them forever. In that way, you can sustain anything in this area up here that gives everybody a payoff of at least what they get in the stage game Nash equilibrium. In this case, that's 0. So that's why we conveniently chose 0, 0 as the Nash equilibrium payoff for this modified version of the prisoner's dilemma. And so anything in this shaded area that gives everybody a positive payoff can be sustained as a subgame perfect equilibrium. Now let's actually verify my claim and see if we can actually find a subgame perfect equilibrium where the average payoffs are indeed 5-1, and along the equilibrium path we have the actions that are played alternate between CC and DC. The way we'll do that is to define a pair of strategies, one for each player, that actually achieves this as a subgame perfect equilibrium. It's going to be a variation on the Grim Trigger strategy. So the strategies are, for player 1, if the history is CC in all odd periods and DC in all even periods, then if it's an odd period, play C. If it's an even period, play D. Otherwise, play D. So this strategy is saying if this pattern of alternating between CC in odd periods and DC in even periods has been going on without any interruption, then continue with that. If there has been any interruption to it, then just play D. For player 2, if the history is CC in all odd periods and DC in all even periods, then play C, otherwise play D. So again, it's similar. If that pattern has been continuing, then you play C. So you continue that pattern. However, if that pattern got broken at some point, then you switch to playing D, and you play D forever. So I claim that this is a subgame perfect equilibrium for these players to play these two strategies. Let's verify that, and we'll use the one-shot deviation principle. We'll start with player 2. After any history where something other than CC was played in an odd period or something other than DC was played in an even period, these strategies recommend the players to switch to D in every period forever after that. Since these two strategies, S1 and S2, dictate that DD will be the outcome in every future period following a history where the pattern was broken, the continuation value for player 2, starting in the next period, it has to be 0. It doesn't matter what player 2 does in period T. If 2 plays D as the strategy recommends, then UT of player 2 is going to be 0. If 2 plays C instead, which is a deviation, UT of 2 is going to be minus 2, because player 2 would be playing C, and player 1 presumably would be following the strategy S1, which dictates that player 1 play D. So player 2's payoff is going to be minus 2. So deviating to C in period T after such a history is not beneficial. So it's not a profitable one-shot deviation. Now we look at the histories where CC was played in every odd period and DC was played in every even period. Now the continuation value does depend on what player 2 does, because if player 2 breaks the pattern, the continuation value in the future is going to be 0. Whereas if player 2 does not break the pattern, then the continuation value won't be 0. We have to do our analysis in both odd and even periods. So if T is odd and 2 plays C, and this is what the strategy S2 recommends for player 2 to do. Remember, player 2, this is an odd period, so player 1 will be playing presumably following the strategy S1, so player 1 will play C. So player 2, if they play C, will get a payoff of 4. The continuation value will be minus 2 in period T plus 1, 4 in period T plus 2, minus 2 in period T plus 3, and so forth. We can write that out as 4 delta minus 2 times 1 plus delta squared plus, which is 4 delta minus 2 divided by 1 minus delta squared. So the total payoff, if you remember from the previous video, it's UT plus delta times VT, because we have to discount the payoff from the next period to this period. 4 plus delta times 4 delta minus 2 divided by 1 minus delta. However, if T is odd and 2 plays D, then player 1 is playing C. So player 2 is going to get a bump to their period T payoff, and they're going to get 6. However, they're going to pay for that because the continuation value is going to be 0. So the total payoff is just 6. So for 2 not to deviate in this period, it has to be that this payoff is at least as large as this payoff. It has to be that 4 plus delta times 4 delta minus 2 divided by 1 minus delta squared has to be at least as large as 6, which is equivalent to saying that 4 delta squared minus 2 delta divided by 1 minus delta squared is at least 2. Well, we can simplify this further. We can write it as 4 delta squared minus 2 delta has to be at least as large as 2 minus 2 delta squared. Or 6 delta squared minus 2 delta minus 2 has to be at least 0. Using the quadratic formula, we find then that delta has to be at least 1 plus the square root of 13 divided by 6. So as long as delta is at least 1 plus the square root of 13 over 6, then player 2 doesn't have a one-shot deviation in an odd period. Now we have to check whether player 2 has its profitable deviation in an even period. So if T is even and player 2 plays C, which is what the strategy S2 recommends player 2 to do, then the current payoff in period T for player 2 is minus 2. The continuation payoff to player 2 is 4 in period T plus 1, minus 2 in period T plus 2, plus 4 in T plus 3, and so forth, which we can write much more simply as 4 minus 2 delta divided by 1 minus delta squared. So the total payoff is minus 2 plus delta times the continuation. So it's delta times 4 minus 2 delta divided by 1 minus delta squared. However, if T is even and 2 plays D instead, so this is a deviation from what the strategy recommends, then the period T payoff is 0, because remember in even periods player 1 is playing D as well, and the continuation value is 0. So the total payoff is 0. For it not to be profitable for player 2 to deviate from C to D as recommended by the strategy, it has to be that the total payoff from playing C is at least as high as the total payoff from playing D. In other words, the total payoff from playing C is non-negative. So minus 2 plus delta times 4 minus 2 delta divided by 1 minus delta squared is at least 0, which is equivalent to saying that 4 delta minus 2 delta squared divided by 1 minus delta squared is at least 2. Or 4 delta minus 2 delta squared is at least 2 minus 2 delta squared. Canceling out the two deltas, we get that this is equivalent to 4 delta is at least as big as 2. In other words, delta is at least a half. So as long as delta is at least a half, then player 2 would not want to deviate in an even period. So if delta is large enough, then player 2 won't deviate in either period. Now we can turn our attention to player 1. We would like to know if there's any period where player 1 would like to deviate. So to show that player 1 wouldn't have a profitable one-shot deviation following any history where something other than CC was played in an odd period, or something other than DC was played in an even period, is exactly the same as what we did for player 2. So we'll just look now at whether player 1 would want to deviate following histories where CC was played in every odd period and DC was played in every even period. So if we look at an odd period, so if we look at a period T where T is odd and player 1 plays C, then the period T payoff to player 1 is 4 because player 2 will also be playing C, and the continuation payoff from period T plus 1 forward will be 6 in the next period because player 1 will play D and player 2 will play C according to the strategies. 4 in the period after that, then again 6, and then 4, and so forth. So that's just 6 plus 4 delta divided by 1 minus delta squared. If, however, T is odd and player 1 plays D instead, then the period T payoff is going to be 6, so they get a bump for cheating in period T, but they lose all future payoff. So the continuation payoff ends up being 0. So the total payoff is just going to be 6. So for it not to be profitable for player 1 to deviate from playing C as recommended by the strategy to playing D, it has to be that the total payoff from playing C, which is 4, plus delta times the continuation, which is delta times 6 plus 4 delta divided by 1 minus delta squared, has to be at least 6. That's equivalent to 6 delta plus 4 delta squared is at least 2 minus 2 delta squared, which is equivalent to 6 delta squared plus 6 delta minus 2 is at least 0. Noting that this is a quadratic on the left side, we can use the quadratic formula to find that this is equivalent to delta being at least minus 3 plus the square root of 21 divided by 6. So as long as delta is at least minus 3 plus the square root of 21 divided by 6, then player 1 won't have an incentive to deviate in an odd period. What about an even period? So if T is even, and player 1 plays D as recommended by the strategy, then the period T payoff is 6. The continuation payoff from period T plus 1 forward is 4 in the next period, 6 in the period after that, 4 after that, and so forth, which is 4 plus 6 delta divided by 1 minus delta squared. However, in this even period, if player 1 plays C, which is contrary to what the strategy recommends, then the period T payoff is going to be 4, and the continuation payoff is 0. We've got the period T payoff as well as the continuation payoff are both lower. So no matter what delta is, it's not profitable for player 1 to deviate from D, which the strategy S1 recommends, to C in the period T. So we've looked at both players' strategies and verified how high delta needs to be for there not to be a profitable one-shot deviation. Note that 1 plus a square root of 13 divided by 6 is higher than negative 3 plus the square root of 21 over 6. So as long as delta is at least 1 plus square root of 13 over 6, then neither player 1 nor player 2 has a one-shot deviation. So S1, S2 is a subgame perfect equilibrium. And for delta close enough to 1, they get arbitrarily close to 5, 1. You can do this for any vector of payoffs that I pointed out earlier. The pattern of action profiles that you have to sustain in the equilibrium might be more complicated than just alternating between CC and DC, but for any payoff vector that we saw in this area of this diagram, that we saw in here, you can find some pattern of CD, CC, DC, and DD. By somehow alternating between these, you can pick out any point in here and sustain those payoffs as the average payoffs from a subgame perfect equilibrium. So as long as everybody gets at least what they get from DD, you can support all of this. It's important to note here that it's not only these payoffs that are on the Pareto frontier that we can support. You could ask why you might want to support these payoffs when you could have these payoffs, of course, but nonetheless the point is there are subgame perfect equilibria that yield these as the average payoffs. For example, you could alternate between this corner and this corner and get the midpoint. So both players would get 2 on average. So there are a lot of different things you could do. You can get any combination of payoffs in here we can achieve as a subgame perfect equilibrium. So we can state this as a formal result, and that's known as the Folk theorem. It's called the Folk theorem because it was well understood to be a theorem before anybody wrote it down as a formal result, hence the folk part of the name. So this is generally true. It's not just for the prisoner's dilemma type games. It's true for any infinitely repeated game. So this Folk theorem says, take any infinitely repeated game and take any Nash equilibrium of the stage game. And suppose W is a vector of payoffs that you get at that Nash equilibrium of the stage game. Now take any feasible vector of payoffs, V. Remember, the feasible vector of payoffs is the convex hull of the payoffs that you can get from each of the outcomes. So take any feasible vector of payoffs, V, such that each player I gets at least what they get at W. Then you can find a subgame perfect equilibrium if delta is high enough, such that the average payoffs from that subgame perfect equilibrium are almost V. The reason I say almost is it's almost in the sense that if delta gets close enough to 1, we get close enough to V. So if we take the limit as delta goes to 1, we get to V. So for patient enough players, we can essentially achieve any of the feasible payoffs that give everybody at least as much as at some Nash equilibrium of the stage game. And the reason we need this part is because we use this Nash equilibrium payoff as the punishment payoff. So you just have some pattern of alternating between the outcomes of the game so that the payoffs average out to V. And if that pattern gets broken, you switch to the stage game Nash equilibrium that yields a payoff of W, and that's the punishment.